So you can see that putting the two methods side by side, and depending on which type of function you're given, whether it's solved for y or for x, it may make more sense to use one method over the other. Generally speaking, you like to keep your rectangles vertical if at all possible. So since the shell method uses rectangles that are parallel to their axis of revolution, you want to use the shell method whenever you have a vertical axis of revolution. And since the rectangles are perpendicular to the axis of revolution for the disk method, you want to use the disk method whenever you have a horizontal axis of revolution. So I'm going to show you another example worked both ways, and you can see why this one might be preferable to one method might be preferable to the other. So we're going to look at this example from 7.2, find the volume of the solid formed by revolving the region bounded by the graphs of y equals x squared plus 1, y equals 0, x equals 0, and x equals 1 about the y-axis. Now this problem could be solved with the disk or washer method, and we did that in the previous section. So let's take a look at it. And you can see using the disk and washer method that this was kind of messy because we had to divide our shape into two different sections and then take two different integrals. And it was all because of those horizontal rectangles and the fact that it just needed to be done that way. However, since we're using the shell method this time, vertical rectangles actually work to our advantage, and we can define the entire shape by the function x squared plus 1. So in this case, my p of x just needs to be x because the axis is x equals 0 on the left of the graph, so x minus 0. And the height of the rectangle is just x squared plus 1. And we're going from 0 to 1. So v would be 2 pi times the integral from 0 to 1 of x times x squared plus 1 dx. And this is a pretty straightforward integral. We'll have x cubed plus x going from 0 to 1. And that's going to give us x to the 4th over 4 plus x squared over 2 from 0 to 1. And then we will plug those in and we'll have 1/4 plus 1/2 minus 0 plus 0, which gives me 2 pi times 1/2 plus 1/4 is 3/4, or 3 pi over 2 units cubed. So here we're going to find the volume of the solid formed by revolving the region bounded by the graph of f of x equals negative x squared plus 4, x equals 0, y equals 0, and x equals 2 about the x-axis. So we have a horizontal axis of revolution. Now, if we were trying to do this one using the shell method, we know that we'd be looking at the form of it that says v equals 2 pi times the integral from c to d of p of y, h of y, dy. And we're going to be looking at horizontal rectangles because they are parallel to the axis of revolution for this method. So for this one, if I'm looking at the distance from that axis to my my shape, that's just going to be the y value, whatever the y value is. Whereas the height h of y, or the length h of y, is going to be the shape, or the formula, but it's got to be solved for y. So if y equals negative x squared plus 4, then y minus 4 equals negative x squared. I'm just moving the 4 over. If I divide by a negative 1, I get negative y plus 4 equals x squared. X would technically be plus or minus the square root of negative y plus 4. But since we're looking above the x-axis, everything is positive for y, so x will actually just be the square root of, I'm going to write it as 4 minus y. Make things a little simpler. So v then is going to be 2 pi times the integral from, and we need our c to d, so that's c equals 0 and d equals 4 for the shape, of y times the square root of 4 minus y dy. And that's what we would need to integrate. And this is doable. We would need integration by parts. Our u would be y, and our dv would be 4 minus y to the 1/2 dy. So du is just going to be dy, and v will be the integral of that thing. We would need a negative out here for the negative, So we would have negative 4 minus y to the 3 halves divided by 3 halves, or negative 2/3 times 4 minus y to the 3 halves. So my integral then will be 2 pi times uv minus the integral of v du. So that's going to be negative 2/3 y times 4 minus y to the 3 halves power minus the integral of v du. So that'll be negative 2/3 times 4 minus y to the 3 halves dy. So we're going to have negative 4/3 pi times y times 4 minus y to the 3 halves. And of course, this is all going to have to eventually be from 0 to 4, but we'll get there. I need the negative for here for this integral, so I'm going to go ahead and just leave it, but I'm going to pull out that one. And we'll have 4 minus y to the 5 halves power divided by 5 halves. And then that's all going to be from 0 to 4. So that gives me negative 4/3, and there was a 2 pi here as well that we kind of lost. Got distributed. So I'll have negative 4/3 pi y times 4 minus y to the 3 halves minus 8/15 pi times 4 minus y to the 5 halves. And then we still have to plug in everything in that from 0 to 4. And that's going to be super messy. I don't even want to finish this, guys, because this is just rough. We've done the integration, but you still need to plug in the numbers. So you can keep going with that. You can plug all that in your calculator if you want. Or we could take a look at the disk method version of this and why this would be better. So for disk method or washer method, whichever one you're on, we're looking at that horizontal axis of revolution. So we're only looking at this portion of the shape from 0 to 2. And my r of x here is just the function, which is negative x squared plus 4. So v, using the washer disk method, v is pi times the integral from 0 to 2 of negative x squared plus 4 squared dx, which gives me pi times the integral from 0 to 2 of, if I FOIL this out, I get x to the 4th minus 8x squared plus 16 dx, which is pi times x to the 5th over 5 minus 8/3 x cubed plus 16x, all the way from 0 to 2. Or we get 32/5 minus 8/3 times 8 plus 32, all minus 0. And when you add those together, you get 256 over 15 pi cubic units. Now you would have gotten the same answer if you had plugged 0 and 4 into all of that. But I think you can see, especially if you look at them side by side, for this particular problem, the washer disk method is superior. There's just no way around it. It's a lot more straightforward. And again, like I said before, that's going to be true for the most part. If you have the opportunity to use a vertical rectangle, you want to do it. So for this case, you would want to use the disk method, and for this case, you would want to use this shell method.